Hey. Every time I make one of these videos, I at the beginning say I'm going to make it quick, and it never ends up being quick, but I will do my damnedest this time. Basically, what I wanted to talk about is stem cells, as in the title, and I want to do it for my undergraduate notes when I took lectures in what is to an undergrad basic biology, and to most people it may well be. A lot of this stuff people may have learned in high school. Certainly, I would have known most of it by what I know in Scotland is higher level. But of course we have a level after that, advanced higher, and this is when they get into the details and the nitty-gritty of this kind of stuff, and of course in first year of uni, if you're doing biology. And I wanted to just talk about stem cells for a bit from my notes, because I wanted to quantify the fact that people don't understand it very well. And people who do know of it and have done their homework in a certain way, you know, I think the stuff we learn in undergraduate could better equip them to argue about it. So that's basically what this video is for. It's to better equip people who already know what I'm on about, and in the hope that I can say something that's actually useful. If it's useful to one person, it's useful. I keep trying to say that to myself. So yeah, that's the purpose of this. So we'll get on with it. Right, so we're talking about stem cells. Of course, we're going to have to talk about embryonic development. I'm immediately going to refer to a crash course video, very well done by Hank, a description of animal development. And the reason it's so important is because, you know, animal development, the embryonic development, isn't just relative and important to think about humans. All animals do it. It's kind of the reason we know that evolution's true, but I'll just let that one fly. He's about 3 minutes in, he starts talking about morulas and stuff, which is really what I'm kind of referencing. Like, I'm talking about the kind of the bit before it, and the fact that by that point the cells are of a different type, different stem cell type, because they're still stem cells. And so if you really want to understand that and relate stem cells to that, that's a good thing to watch. So about 3 minutes in, I'll link it below and try and give like a time as to when he starts talking about it as well. So we'll go from the beginning. Embryogenesis, sorry. You're starting with a zygote, you're starting with your diploid blueprint, created from your haploid cells, from your egg and your sperm. I'm initially going to say to you the reason that the egg cell is so large is because once this zygote is made, it is not going to synthesize anything up to number 8. And when I'm going to talk about numbers, I'm going to talk about cells. It's the number of cells that I'm referring to. So basically this cytoplasmic volume will not be added to throughout the cleavage process. Most people know what I mean by that. That is the first mitotic processes. You're talking up to number 16 of cells, okay? And that's the first cleavage. And basically nothing's added. So each time it divides, you know, 1, 2, 4, 8, 16, 32, right? Each cell gets smaller and smaller because they're divided with the same amount of stuffs, basically, particles. And that's important to note that. That's why it's given a different name, because it's kind of doing it on its own. It's very fragile. If any one of those cells is lost, the whole thing will fail and it will die. That's why so many, like pregnancy isn't so important, because those cells can die, and that's within the first day. I mean, even if fertilization does happen, there's still a high chance that it will die. People think that there's just a high chance that, you know, fertilization won't happen. No, it's that it will die very quickly. And I don't mean dies and it has a sense of life, it won't succeed, it won't be successful. People don't seem to understand that. You know, people want to start claiming fertilization as the point of life. Totally wrong, totally biologically wrong. You go back to school. Okay, so we're talking about from stage 8 to 16. It marks the important point in the development. because any cell from that stage can become an embryo in its own right. Basically, zygote to number 8, very fragile. At number 8, it starts to create its own little skeleton within cells, and cells do have inner skeletons, and that's the point when it's kind of becoming enforced, and therefore it's not as fragile. So that's when it starts to basically decide what it's going to do. From 8, it can still become its own embryo, like that's when twins can happen. Like one can break off and start a whole new embryo all of its own. But after number 16, after that stage of 8 to 16, they can't become embryos anymore. They become fated in a way. And there's a level of fatedness, and that's what I'm going to discuss. This is when discussing them as stem cells begins. Because a stem cell is one that has a potential to differentiate into a different kind of cell. It can be one thing and become another, basically. It doesn't necessarily mean that it can become any kind of cell, as people seem to think. It may have a certain level of differentiation already imposed on it, and that's what we're talking about. 8 to 16, it's not imposed to do anything in any way, but after number 16, immediately, when it jumps from 16 to 32, each of the daughter cells that come from that, one of them's going to go to the membrane that will form around what it becomes the blastocyst. If you understand the embryonic development, you understand what I mean. So that's the trophoblast, is the membrane around it. And then there's the cell mass in the middle, which is the actual blastocyst itself. And that's added to by the other daughter cell. So basically each one splits. One becomes the membrane, one becomes the mass. One becomes the membrane, one becomes the mass. One becomes... And it happens all at the same time. So it's quite kind of difficult to think of it that way, but then what will happen is the trophoblast on the outside is going to become your placenta. That is fated to become your placenta, and your inner mass is less fated than the trophoblast, but they're still in the same classification. They're still fated in the same way by biologist standards. The trophoblast can become any part of the placenta, any part of the connection to the mum and baby, but at this point it's not embedded, it's not implanted. So it has the potential to become something else, but it is not yet something else, so it's still a kind of stem cell. The mass in the middle, what it's going to immediately do is start creating fluids, and that's going to be the bag around the baby. It's going to be the water breaking when a woman goes into labour. It's all that fluid that's been made up over time and maintained over time, and that's what the inner mass initially does. But it will eventually be the cells that become the baby. That's in the way it is a stem cell, because it can either create fluids or it can become the baby, basically. It can't become another embryo, and that's really important. At this point, having twins, out the window. If it's not done it by now, and there's very few cells to be doing it from 8 to 16, that's 8 cells to be going off and doing their own thing. That's that. So when people say, like, you're killing a baby, when researchers take the cells, they're not taking all of the baby, because any one of those cells can start again and become the baby. So it's really daft to say that, and it will have the same genetic code, so it's really daft to say that you're taking the baby away. You're not even taking part of the baby away, because it can just start again from 8 to 16. And that's the point where they want to take these cells from, because any point after that, and those cells are not useful to be taking them, so they wouldn't take them. They would just let the baby develop as if it was going to succeed at all. And you can put any of these cells into a human body, any of the 8 to 16, and they will just form part of whatever they're put into, whatever they settle into, and they will become a normal cell. Of course, I mean from the same genetic code, otherwise it would get shifted out by alien, processes. If it's an alien, they get chucked, basically, to put into another body. But that's a whole different topic about using stem cells in other people and things like that. And part of the reason it was so difficult was because they had to be a genetic match in a certain way, not just in the same way that blood type is a match, but in far more complicated way and manner, so that the body didn't reject whatever stem cells they were trying to use. And that's why it was so important to get the development going, because without it, it was never going to be an application, it was just an idea. That's something completely different topic. There are stem cells in adults, and that's an important fact, because after number 16, those are considered adult stem cells. They have a point in repair and regeneration, and basically they're already decided on what they're going to become in a certain way. When I was talking about the different potentials to differentiate, that's what the biologists use to classify the different stem cell types. There's your embryonic stem cells and your adult stem cells. There are 4 types in all. Go through them. Totipotency, because all these are potencies of potential, potencies of differentiation. Totipotency, pluripotency, these are your embryonic ones. Then you've got your multipotency and unipotency, these are your adult ones. I'll explain each one. Totipotency, every cell from the zygote right up to number 16, so that's the ones that can form a baby all of their own right. And then your pluripotency is when they can, become part of the trophoblast or the blastocyst, and that can become anything on after there, but it cannot become another embryo. That's important differentiation. The second types are the adult types, and the reason they can't be used and aren't developed, because I know someone would probably catch me up on that, is because it's a different kind of potency. The multipotency, it means it can form into a different number of cells, but not a different cell type. Basically, so here's the word I never get. One of the best examples is, of course, bone marrow, and that's something I'll talk about. Hemopoietic stem cells, I think that's the word, and that is reference to the blood. The heme, of course, the hemoglobin, the hemopoietic, and that's of the bone marrow, and they can differentiate into red blood cells, white blood cells, the platelet stuff, all that kind of thing, but it's definitely going to be part of the blood. It's differentiated into it's going to be part of the blood. Unipotency is a further step on top of that, where basically the only difference of what it's going to become is whether it's going to have a certain set of proteins or another set made afterwards. Things like myoblasts, which are muscle stem cells. And basically, you're talking about your arm, and it can either contract or relax. Within one muscle, there will be lines of ones that contract, and there will be lines of ones that do the opposite. I know people talk about the 2 muscles, but even within each muscle, there are different layers. And basically, when a myoblast is forming, basically what it's going to do is it's either going to become the one that stretches and allows for elasticity without, going too far, and the other one's going to be contraction, it's going to pull together. And those are different proteins within different muscle cells. So it could be a different cell, but it's still not a different type, it's still a muscle cell. And that's the point, like the myoblasts from your arm can't be put in your heart and things like that. You would need to go the step backwards to multipotency to be able to take a muscle cell that is multipotent and be able to make a heart out of it and things like that. But really, when you're making heart, you really want to start further back in potency, because otherwise it won't form a whole heart and that kind of thing, because that's what a big thing that was talked about, was making hearts. Nerve cells, another thing, there's applications in Alzheimer's and Parkinson's and all that kind of stuff. Cystic fibrosis, different lung lining cells, basically. Loads of different applications, but you have to start further back or it doesn't have the ability to become what you want it to. And that's, of course, what I was describing. And that's on the level of significant applications of what we could use this for. And I know whoever watches this will probably know this stuff, because they wouldn't have watched this video otherwise. You know, I mean, we already use bone marrow transplants, and you know, use of moving skin to different places, things like that. I mean, that's a use of the skin's multipotency to be in any other place, basically, um, to form the edges and to form over burns and things like that. I mean, I could talk about the sources for the embryonic cells and stuff, and that'd be a different discussion. What I'd like anyone who's watched up to this point to take away from this video is this little speech that I've prepared for the end. It's the importance of why it has to be embryonic cells that are used for these applications. You may not understand that, you may not have known beforehand that adults, you know, the terminology for those different cells was that they were stem cells. In essence, stem cell research wasn't slowed down at its beginning when it was first starting out and it can never achieve anything. It's already achieved lots. It was slowed down decades after its initial application being things like bone marrow transplants. And I would hope that that might make someone think twice about being against it, because, you know, I haven't addressed the sources of where it could come from, but it isn't blending babies. It's using cell abilities. You don't have to use babies for that, and to talk about that properly, I'd have to talk about the sources for embryonic cells, to cover that properly. But yeah, I hope the whole thing where I said basically if you took any one of those cells away, it wouldn't matter, because from 8 to 16 it could become its whole own little baby if it really wanted to. And here's the thing I want to leave this video with. When the blastocyst and its trophoblast, that blastocyst part, the soon-to-be fetus, becomes implanted within the uterus, the blastocyst is about 250 cells big, and what I was talking about was, you know, cell number 16. I mean, if that doesn't, you know, create the big difference that there is, I don't think people get it very well. You know, talking about taking it from fertilization and stuff. It's 250 cells big before it's a child. And even then it's not a child till like months and months after, because it has no sense of what's around it and no differentiation between cells. There's nothing about it that is human. It could become a sponge for all it cared. The only thing that makes sure that it doesn't is its, you know, genetic code. And if you really want to protect its genetic code, then you better be protecting all the sperm and egg cells in the whole wide world as well. Because each one of them is a genetic modification and change and, you know, mutation on its original, and therefore apparently unique. People might say that at number 16, them being less of them makes them more important. Biologically, that's false. At that stage, they can always make more. They can always, you know, become another baby. They're totipotent. Remember, that's the important part. They're totipotent. So anyone that would use this to further arguments with someone, remember to say that they're totipotent. They can still become a baby no matter how many you take away, unless you take away all of them, which you wouldn't do, which would be talking about sources. So yeah, I hope this helps someone argue or make the right points, make the points more informed. And it's gotten dark over this video, and it's a really long video again, so I'm very sorry, but I hope that helps you think about it.